Okay, well, why don't we go ahead and get started?
Sounds good.
All right. Uh, Welcome everybody to our newest research seminar. We have with us today Daniel Kilo from the University of Wisconsin-Madison, who's going to talk to us about towards building accessible virtual worlds, developer challenges meet post hoc solutions. Daniel is a third-year PhD student in Dr. Yuheng Zhao's Mad Ability Lab. He combines HCI, XR, and AI to create accessible systems for people with disabilities, particularly blind and low vision users. He's presented at top conferences, including CHI and Assets, and we're very grateful to have him with us here today. So, Daniel, please take it away.
Yeah, thanks so much for having me, Dylan. Good to see everybody here today. Um, Again, my name's Daniel Kilo, incoming third year PhD student at University of Wisconsin-Madison. Thank you for joining me today. I'll be covering two of the projects that I've been working on over the past 2 years or so. On this slide, I'm now screen sharing a like Google Slides PowerPoint presentation showing the title of the talk, Towards Building Accessible Virtual Worlds, alongside a picture of myself, kind of a white male presenting individual. I've got long brown hair or brown hair with blonde streaks. And I've got some logos from our lab, the Mad Ability Lab, University of Wisconsin-Madison, and the National Science Foundation. Um, I've got today's date, July 16th, 2025, and a mention of XR access as well. The other teaser image that I have here on this slide is illustrating a few of the different interaction methods that we'll be talking about later. So each of these are teasing a different component of the post hoc uh, uh, virtual reality description tool that we've developed. It's segmented into four different sections. On the left being image A, showing a basketball court with a labeled avatar, an interactable basketball, and like a hand and a like portal that you could use to teleport to a different world in the background. Also on the slides, an audio or on that image is an audio description pop-up reading, "There is an avatar standing on a court with a basketball, and a portal is visible in the background." Also on this slide after that is image B, showing a room with a menu and a number of labeled portals. Three of those objects are labeled. We have one marked first, which is on the leftmost side, reading a sign expressions. So reading out that there's a sign there with the label expressions on it. Kind of a little bit to the right of that and above it, so sort of like behind it in space, is Portal to Starlight Farm. And to the right of that is one marked third saying Portal to Murder. Um, on the next image that we have, image C shows a room with multiple different avatars in it and an interactable object close to you that's described as orange circle, white border symbol inside. Sorry, white border symbol inside. Kind of describing a like an orange frisbee that you're holding. And then finally, image D on the fourth image displays a settings instruction panel with a few different labeled interface elements, showing a sound effect playing when a hand is approaching an out of bounds marker. So there's an audio or a warning sound effect when the hand is going out of bounds. So yeah, I'll go ahead and continue with the presentation, but real quick, just wanted to give a thank you for everybody again from joining, particularly anybody who may be joining us from like East Asia or Australia right now. I understand it's quite late for you all, so hope everybody finds the talk valuable. Um, Again, about me, third year PhD student, working with Yuhang Zhao. I got my bachelor's at the University of Texas at Austin, and I worked on some projects there with Amy Pavel, who's I presented a previous assets paper with. And I also worked in the Texas Immersive Institute with Professor Aaron Riley, doing a number of projects there, which I'll get into on the next slide. But some of my general research interests nowadays include human-computer interaction, accessibility, augmented, mixed, and virtual reality, and generally using artificial intelligence and computer vision models to make these systems more accessible. Um, the Some of the work that I've done at UW-Madison primarily involves like XR accessibility. So I demoed one of the projects that we'll be talking about today earlier this year at Chi. Um, I also have an upcoming project that uh, and is similar. There we will have another presentation for that soon. I can't disclose any more than that because of the anonymous submission policies, but we have an upcoming project there, and then I also have some work in the past on eye tracking for people with visual impairments. Our lab does a lot of work with cooking. So one of those projects was Chi 24 work I worked on with my lab mate Ru Wang, and then a cooking paper, which is upcoming later this year, hopefully. The final thing I have shown off earlier this year is a mixed reality drift paper that was also a poster at Chi. And that hopefully helps sighted individuals correlate where digital objects and their physical representations should be in mixed reality. At University of Texas, I presented a paper at Assets about 2 years ago on making live videos. So like TikTok live, Twitch live streams, or like YouTube live, more accessible for blind individuals. We had a number of expert describers, so experts in the field, generate manual descriptions for that sort of content, and played them back and evaluated those with blind users. And then kind of final project at Texas was that I'll talk about is a skin cancer prevention project where we used augmented reality to show young people that skin cancer is something that they should care about, even if they're like 18 years old. And then a long time ago, I worked on a project exploring virtual reality for oral placement therapists. So that's like speech therapy for typically for like children with Down syndrome. So we worked with therapists to help them basically do their job a little bit more effectively, potentially using VR as a training mechanism. I will now go ahead and go into the agenda for the rest of the talk. So the overview, just to start, I'll go into two different papers that we've gone over. So firstly, XR for All, Understanding Developers' Perspectives on Accessibility, Integration, and Extended Reality. And then how that paper informs my most recent work, VRSight, which is an AI-driven scene description system to improve virtual reality accessibility for blind people. This is the first time I'm presenting either of these papers in an official capacity, actually. So yeah, thanks again for joining us. After talking about both of the systems, I'll do my best to do a quick live demo of VRSight. And I believe I'm sharing audio now as well, so we should be able to hear some of those descriptions. And then I'll go over some opportunities for future work. We are looking to open source VRSight as soon as we get confirmation on a conference acceptance. So hopefully we can have other developers in industry or other researchers kind of improve on the interactions and encourage other developers to be attaching their applications to VRSight as like a user-sided system. So, and then we'll have an open Q&A afterwards. So without further ado, I'm going to start now with XR for All, Understanding Developers' Perspectives on Accessibility, Integration, and Extended Reality. This is a project I worked closely with Tiger Ji, Kuxin Zhang, Yaxin Hu, Yu Huang, Roufei Du, and my advisor Yuhong Zhao. You might know Tiger from VR Bubble, which is a previous virtual reality accessibility work, kind of like proxemic spatial ear cons, so like sound effects when people move within range of you in like a social VR environment. And so that this project was kind of started around that time, around like 2022. And then Tiger got his master's degree, and I kind of took it over from him about halfway through 2023. So as you all are likely aware, developers kind of don't consider people with disabilities like, or there seems to be this perception of maybe a typical XR user that doesn't necessarily, quote, need accessibility support, or maybe has disabilities that aren't impacting or that aren't necessarily impacted what others would consider as needing accessibility support. For example, like I have an invisible disability, like considered invisible disability, or like a chronic illness that doesn't severely impact like my day-to-day usage of like my visual impairment like every single day, but developers kind of have this like quote average user necessarily that they kind of like target. And so with that in mind, like uh, people with disabilities face different XR challenges. We're talking about like navigation, exploring virtual or physical environments that are augmented, as well as like object identification or mixing audio. So that's like real world sound effects mixing with digital sound effects, and then uh, distinguishing between those. And at least I believe that XR growth is really contingent on this ability to have available technology and including additional people into the into this eco in or this environment. And that's what I'm sure. And this is an XR Access talk, so I'm sure all of you likely feel similarly. But you know, having these accessibility features, even if they're just developed towards certain groups, often make the user experience more accessible or just better for everybody. So after talking to some developers here, or prior work really, um, looking at some of the existing development challenges, we kind of have this lack of XR specific guidelines. So in 2D environments for like web development, there's this well-explored themes, or there's these well-explored themes of like web content usability guidelines, if you're familiar with like WCAG. Um, they that organization and many others have these kind of guidelines that users can follow in order to make their websites and other 2D user interfaces more accessible to people. Similarly, there are some for 3D virtual worlds, but not all of them are super applicable to extended reality environments. Maybe that's just because of the first person nature of a lot of XR applications, whereas maybe a 3D game like Fortnite, for example, has a third person camera over the shoulder rather than like kind of behind you, rather than you embodying the character. Additionally, although that some research groups and organizations, I believe XR Access might also have some preliminary guideline resources as well. Are there are these sort of aggregation bodies, but they're largely fragmented with varying standards to what users would consider accessible or not. And one of the main other things that developers kind of cite are lack of time, like lack of funding resources, maybe legal issues, things like that, that really they claim like prohibit them from really making their experiences accessible. So in order to tackle these challenges, we devised a few different research questions. Research question 1 was, what challenges do XR developers face against developing XR accessibility features? Research question 2, what current XR development practices do developers follow, and how would their practice affect the implementation of XR accessibility features? And then question 3, how applicable are existing state-of-the-art guidelines for 3D virtual worlds to XR? And what support methods would best enable XR developers to implement XR accessibility features? We'll be focusing today on that third research question, more talking about the guideline evaluation, and also talking about some of those support methods as those support methods kind of motivate uh, the VRSight, the second paper that we'll be talking about later. So in order to answer these questions, we interviewed 25 XR developers. Some studies call them practitioners rather than developers. But these developers all had roughly 2 or more years of XR development experience. I believe our average was about 5 years of XR development experience at the time. We did also explore company sizes from freelance individuals to big tech companies. We consider like a freelance individual to be somebody working for like a particular client until the scope of that project's filled. We evaluated like startups or people working at startups as like independent companies of multiple employees. Maybe they have specific roles, but one developer often shares like multiple responsibilities, and there's not really an accessibility or a legal team at that company. One example, at least at the time of the study, would be like VRChat as like maybe a really large startup, but still like falling in this category. We'd consider more like a mid-size company after that to be a catch-all term between more mature companies, game engines, universities, and medical facilities. So mid-size companies shared like some characteristics between startups and big tech, but maybe they have an accessibility team, for example, but it's like quite small at only like 2 people. One example of that could be Unity software, the game engine. And then big tech we consider to be more established large technology companies that often have those sort of dedicated teams. And if one developer has multiple roles, it's typically wrapped up in a more general like job description. One example of this sort of company could be Microsoft. Um, Most of these XR practitioners had mixed prior accessibility experience. We didn't require that they had any, but most of them uh, did have some amount of accessibility experience. If you'd like the full table, it's included in our paper, which is on the talk description page. But we did have one participant, for example, who had less XR specific experience, but was working specifically on accessibility at a game engine. The method, once we have aggregate or for each of these developer interviews, we asked all of them to present a past XR project to us within their own engine. So that kind of helped us understand their average workflow, covering topics like how did they typically set up a development environment, how do they organize their scene hierarchy, what naming practices do they follow, stuff like that. We also asked them any like existing limitations that they had against or like against accessibility integration or anything that they felt would prevent them from effectively implementing accessible features into their products. We also asked them to like generally their affinity towards third-party packages. For example, what packages they had installed, what sort of like templates do they follow, things like that. We asked them, and on the next slide, I'll get into some like guidelines that we had them follow and how we got into that. But we did have them evaluate helpfulness of existing guidelines for 3D virtual worlds and some budding XR guidelines at the time. And then from there, after covering some of these accessibility terms, we asked them to suggest some of the things that would be best support methods for them, what tools might support their development, and what tools might help them generate these or develop these accessibility features, and then also at what stages of the development cycle. So, in order to have the developers evaluate guidelines, we aggregated from a large variety of 3D games or 3D virtual worlds resources. I believe our Total at the time was around 12 different resources that we felt were mature enough to uh, look into further. And then we ended up narrowing that down into six. So that those six resources are the game accessibility guidelines, W3C XR accessibility user requirements, the designing accessible VR instructions from Meta for the Quest platform, the accessible player experiences guidelines, the Xbox accessibility guidelines, and the IGDA GASIG top 10 guidelines. Synthesizing these together, we devised 25 or 20 different guidelines to have users evaluate under visual, so 5 for visual, 5 for motor, 5 for cognitive, and 5 for a combined speech and hearing impairments category. These categories enabled us to interview developers in one of these different categories and really dive into implementation details and what they thought about each of these guidelines within a reasonable amount of time for an interview. So some of the feel that we got for these guidelines or these responses after interviewing these developers, some of the things that would help them would be dedicated feature examples. So if we provide sort of an accessible and an inaccessible version of a general guideline, let's say that the guideline is that we don't want to have flashing lights in our or strobing effects in our applications for fear that it might impact somebody, or not for fear that, but because it may impact somebody with photosensitive epilepsy. So in that case, maybe we'd provide sort of a video or just like any sort of animation that demonstrates an accessible strobe rate, or as well as an inaccessible strobe rate. And maybe the inaccessible one is like you have to click behind it and like verify it with some sort of user interface that really allows the developers to say, okay, something like one strobe every second is okay, but something that's like 15 times a second is like really not. A lot of our developers didn't really know where that line was for what was okay and what was not. Not only with like video examples, but developers also wanted code snippets. So let's say that they maybe could tell generally, like visually or with like an audio sound effect, like what something should sound like or what something should look like, but they didn't know how to implement it. So having downloadable projects or Unity scenes that they could take and then adapt to customize for their project would be very helpful for them. And then finally, also talking about making guidelines easier for developers to implement, we're thinking about blog posts. So sort of those best implementations, having a description of each of the performance costs, as well as a relative importance per development phase. So if we're having a guideline be implemented more as a design element versus a like maybe it's more important that you get it done as soon as possible when you're building out the app, having some sort of flag there, rather than having a guideline that could maybe be a settings toggle that's more of like a user interface development where a thing later in development that you maybe should outline in the design phase, but you don't need to implement it until closer to the testing phase or when you're shipping the product. The additional things that some developers supported, so we ask like, how can we best support developers in this case, right? Like, so even if we do create these external accessibility support packages, like will developers even use them? Some things that developers talked about was that they prefer reusing internal code. So anything built inside of the company rather than just taking something from outside or online. So internal code, templates, or plugins, something like that could just be like a player component or the XR rig from a previous project, as well as things that are free, downloadable, open source, easily implementable, qualified from the company's legal team, and easy to maintain. And we have a quote on this slide from P23 saying that good software tools are very minimal in terms of their implementation time. If a tool takes 25 hours to implement into your application, that's misery. If it takes 25 minutes, that's an actually good tool. A tool needs to be able to be picked up and used quickly. In addition to guidelines, though, we still have this pain point where third-party toolkits need to go through strict review from those internal legal teams and comply with their standards. So in that case, or with that in mind, that requires kind of this independent implementation, not only per team, but also per app. So for each product that's being made, maybe there's multiple levels of approval that it needs to go to, which is very time consuming to include, develop, and refine over time. Therefore, we kind of pose this user-sided post hoc tool to kind of build more of a foundation into what's considered as a average VR user, and that allows us to really motivate and mobilize this area without needing specific developer support on the front end. So with that in mind, I'll now pivot over to VRSight, which is our second project. VRSight is an AI-driven scene description system to improve virtual reality accessibility for blind people. This is a new system from the ground up that we're aiming for anybody to be able to just download and run on like a gaming laptop and a connected headset just with like a really long USB-C cable. So this project was led by myself, Daniel, and then I have 4 undergrads / industry professionals helping me with this project: Justin Fung, ZX Ching, Daniel Wong, and Ritvik Dyava, as well as 2 collaborators on this project, Yapeng Tian, who's more of a computer vision expert, and then my advisor, Yuhang Zhao. So although the previous project focused on augmented, mixed, and virtual reality, VRSight primarily focuses on VR scenes and social VR. As I'm sure a lot of you are familiar, virtual reality uses a combination of visuals, audio, and haptics to really immerse users in these like fully digital environments. However, the medium to which to convey like interactivity and these things, or objects to pick up or directions, a lot of the times are primarily visual with no sort of haptic or sound effects to really guide you towards those objects. Maybe there's some haptics when you're getting close to an object to pick it up, but if you're somebody who maybe even has difficulty wearing a VR headset with your glasses on, then it may be more difficult to use the platform as a result. So most VR apps kind of use these like visuals to convey like signs, outlines around objects. And not only that, but they also lack common assistive technologies that we might see in a 2D interface, like a screen reader, to effectively discern these objects, perpetuating this perception that like, oh, VR is not for this group of people, right? On this slide, I have a few teaser images of VRSight. So I'll get into each of these a little bit more later, but there's 3 images stacked on top of each other. The topmost one shows an image of our object detection model with a normal VR scene screenshot with a bunch of boxes around each of the interactable objects. So there's 5 different interactable objects highlighted and then 1 button on top of a table with 2 hands reaching out towards the table. Slightly below that is another image with a heat map. So basically, if things we've detected that they're closer to you, they'll show more of an orange color. And then as they get farther away, we get more purple or black. So if with this image being 2 hands reaching out towards objects on a table, the 2 hands are quite close to the user, but then objects at the back of the table are much more purple or black. And then at the very bottom of this slide, we have some different sonification objects, or some sonification indicators. So if the objects are closer to you, we use just volume to communicate to the user's different proximity. So it's louder if it's closer to you, and it's quieter if it's farther away. And then we also estimate the spatial position of each of these objects just from reading the screen detail. So if there's an audio object that's a little bit more to the left, then it'll also play a little bit more in your left ear rather than in your right ear. So going into the next slide, our VRSight is kind of our post hoc screen reading system. One thing that we think is really important about this system is that we don't need developer intervention. It's all user side. We're using the latest artificial intelligence models to identify in-scene objects, estimate their position, and then communicate that information to you using directional audio or spatialized sound. The system does use off-the-shelf hardware as well. So again, you don't need to buy anything other than right now for our implementation, there's like a 3-key keyboard, but it's a maximum added cost of like $15. On the right side of this slide, I have another image just with the same 2 hands reaching towards a table, but we have a generated audio description from the application reading 2 hands are reaching towards interactable elements on a table beneath a sign with instructions. So pretty similar to how I would describe it on the previous slide. We also tone match the speech. So if the speech is more, if you're playing up maybe a horror game that's a lot more scary or frightening, then we will make the tone of voice sound more frightening as well, rather than just sort of a flat neutral object, or as a flat neutral tone of voice. To implement VRSight, again, we use a multitude of different models to process the input VR gameplay. I have a system flow diagram demonstrating the input VR video frames as well as the user interactions with a 3-key keyboard that we've taped onto the left VR controller. Each of these video frames go into a few different models, which I'll explain on the next slide. And we use that information to do different sorts of object detection. So different objects position, generate like a 3D position for that object, generate what the object should say or what the description should say, and then attach a tone to it, generate the audio description, and then filter out which ones we should read to the user based on the interactions that you do. And then all of these are communicated back wirelessly to the headset through like a background audio utility, which you can get to just with the web browser. So in order to detect these objects, we use a computer vision model called YOLO V8. If you're familiar with YOLO, it's like one of the more popular chains or like different systems that allows you to like give it a single image and then it'll identify each of the objects, draw a colored box around it, and explain what that object is. So we combine this object detection with the depth estimation from another application that we're using called Depth Anything V2. We take that, and then we also have line extraction, which is just like a base OpenCV code that allows us to estimate where a user might be pointing with their virtual laser pointer in VR. And then take all of these different models in order to do that sort of real-time audio generation. The one kind of main quirk with using object detection models, though, is that it will only detect the classes that you put into the model or you feed into the model. So the base YOLO, like the base information that YOLO is trained on is, to my understanding, COCO, which is common objects. What is it? Common objects in context, which is around 80 different commonly seen object classes in a real world setting. So maybe that's like cars, it's people. But in this case, since the virtual reality environments look so different, that same object or that same image with the two hands reaching towards the table doesn't identify anything in the scene except for one of the objects as a cell phone, which the object is not a cell phone. It's like a game cartridge with an image of a gun on it. But not only is it misidentifying that as a cell phone, it's also not super confident about it and not identifying anything else in the scene. So with this in mind, we developed the DISCOVR dataset. In order to generate this dataset, we hand annotated or we recorded and annotated footage from 17 mainstream social VR applications and demos. These images ended up totaling to 17,691 of them. And from that, we sort of coded 30 different VR object classes across 6 categories. These applications end up or enabling us to take that one cell phone object and get like signs. We have different types of interactable objects and like hands, for example. So on this slide, I'm now showing a side-by-side comparison of the YOLO output or the COCO output and a new model trained on our data set. So of these 30 classes, we have between 124 and 14,375 instances per class. Sort of at a high level, we've then like combined these categories into a few different areas. Maybe those are avatars, including like avatars or chat bubbles, informational things, so signs or UI elements, interactables, so buttons or targets to shoot at or press. Safety features, so if you're walking out sort of outside of your defined play space, we're able to identify that and lead you back in. Seating areas, including like seats and tables and like campfires, sort of these more collaborative environments. And then our final category being VR systems, so that's things like your hands, your controllers, or the dashboard. I am now showing a graph of each of those different classes. So the best class that we're able to get an average precision of almost 0.7. So seemingly like very high, pretty much always we're able to define the out of bounds object or the out of bounds objects and the guardian objects very consistently. So anytime that your hand is going outside of the environment, we're able to detect that pretty much all the time. The things that are also pretty good are like chat boxes or menus or user's controller. And things that are maybe less easily identifiable include locomotion target, especially, which is if you've ever tried to use VR and with like a teleportation mechanism where you maybe like press the thumbstick forward and it teleports you somewhere, the ring on the ground is what we're trying to identify. And the ring on the ground ends up either not being identified as maybe just some decoration on the floor, or it's not. It's either misidentified or it's just not identified at all. And I see some questions in chat, and I'm trying to wrap this up quickly so that I'll be able to get to the questions shortly. In order to evaluate VRSight, we do we've devised 4 different default interactions as kind of a top-down approach. So we start with a more general like overview scene description using like GPT-4o, so like ChatGPT's like system interface, and that allows us to just feed it the image and generate like a 2-sentence description of generally what the user's looking at. From there, we feed in those, if the user presses the slightly more specific button, we activate scene sweep, which is a multitude of like object level short descriptions, which we sort left to right and play out in spatial audio to try to help users locate each of those objects in space. Thirdly, we have aim assist, which is also object level descriptions, but they're localized around whatever your hand is over or whatever you're pointing at. So if you're using a virtual laser pointer, we attempt to identify that laser pointer and then read out whatever you're pointing at. And then finally, we have a feature called Safeguard, which to our understanding is completely novel, allowing us to play a sound effect if you're close to the boundary location. So on this slide, I now have those same descriptions from the very first teaser image slide. A, giving the general scene description, there's an avatar standing on a court with a basketball and a portal is visible in the background. B being like the second image being sign expressions, portal to Starlight Farm, portal to murder, each playing a little bit spaced out from one another and also with spatial audio. Aim assist, the third image would be interactive element, orange circle, white border symbol inside, talking about a frisbee that a user is holding in their hand. And then finally, the safeguard feature being notifying the user when they're going out of bounds. We did some generalizability testing internally on 12 different apps. We found generally that apps with a contained amount of images that are also in the data set tended to perform really well. We weren't totally surprised by this, but Oculus First Contact, for example, is just one scene that plays out for about 20 minutes. And that very consistently only identified the objects in our data set very well. However, we did experience in Roblox, for example, like one particularly bad case where a radial menu popped up, and we were able to identify most of the different signs that came up or UI elements that came up, but reading all of those out individually is really fatiguing, and you have to read everyone out individually from left to right. And if there's like 20 different objects identified on the same frame, then it takes a really long time to read those out. Additionally, some issues that we ran into with the pointer or the line detection in particular. In order to run some user studies, which I'll talk about shortly, we tuned the pointers for like Rec Room, which is one of the popular virtual reality applications. So in cases where the pointer just doesn't look like the Rec Room pointer, we oftentimes weren't able to accurately get whatever the user's pointing at. So maybe we recognize the object, but it doesn't get the whole line, or there's different lines, like maybe it's identifying the floor instead of the user's laser pointer, things like that. We did evaluate VRSight with 9 blind and low vision individuals. Most of them either had no VR experience or very little VR experience. Again, all these users were at least legally blind. 5 of them we consider or were fully blind, and then low vision, meaning like maybe they have glaucoma or tunnel vision or anything like this. That is, almost all of our users came in with either like a guide dog or a white cane, or just to give some perspective on what we mean by blind users. We had each of these users do 4 different tasks. So on this slide, I have some images of each of those tasks. On the top left is we asked users to identify a bunch of different objects in the room, as well as point in what direction those objects exist, and then counted the number that they got right. We then had 2 different combined menu tasks. So we considered it one menu task, but had them do 2 different parts of it, basically locating a specific icon on a menu using the system. One being like locate a backpack icon on the main menu of Rec Room, this social VR game. And then another one locating a specific like join button on the interface. And we gave users 5 minutes to complete each of these tasks. In the rest of the tasks, we had users join a public environment. So there was some degree of variability with other users in the space. So on the lower left of this slide, D is in the lounge environment, one of the base Rec Room applications. And we asked users to count the number of avatars in the environment. So using the system, maybe they could use also other audio cues like people walking around or like trying to wave at them or haptic feedback or anything else to try to use all of these context clues as a whole in sort of a simulated real world environment. And then the fourth task, we had people locate an open seat to sit down in. Doing some pilot studies, we found that blind and low vision users were interested in or had challenges in finding like somewhere to sit down in a conference room. So, or noticing like which seats were open in a space. So we asked users to find an open seat and then sit down in it using the VR controller. And then the final thing that we asked users to do is do an exploration, like a free exploration in this like spooky Halloween environment. So they had 10 minutes to just walk around, explore, communicate what their thoughts were on the system and sort of like free form explore this area. Let us know like what they thought, things about that. I Ken now was planning to do a live demo. I'm not sure what Dylan's thoughts are on that. We are at 12:48 right now. I can pull it up, but it's probably going to take me a few minutes to get that set up and ready to go. I can
Yeah,
also just do it on like an image if we prefer, but
I think my inclination would be to do a quick demo, maybe on a still image, and then
sure.
transition to Q&A. Because I think there's a lot of
Yeah,
questions in chat.
okay, for sure. So yeah, let me quickly so let me just grab a similar, or like, so let's say I have an image that is, um, here, I can switch my screen share to just that screen as a whole. And so what we have here are um, the next slide that we haven't gotten to yet. I'm going to launch this system. Oh, sorry, one moment.
Fancy animated background you got there.
Thank you. Um, So instead of using it on the full VR scene, basically we have this open broadcast software is what I use to basically spoof a webcam. So we take the virtual reality input, uh, fake that it's a camera, and then use that image data in real time. So like as I move this image around, it'll also automatically update on the system in real time. I also realized that I need to update. So in the code here too, I guess I can leak some of the code because we're planning to open source this. Basically, I just got an error because I don't have the like my other webcams like in use right now. So I'm just gonna switch this index real quick, and that's all you need to do in order to switch which camera you're talking about. So um, let's see. Uh, And so again, I'm planning to open source this. Hopefully we'll get word back by the end of the month. But that would allow anybody to use this system and make changes. It'll be live on GitHub, everything like that. We see in this case, so like we are identifying we have a person, it's identifying, this is actually using Coco actually. So this is another demo. So we can also quickly change which model we're using. So the base model in Coco, for example, on this image of one hand reaching out towards an environment shows like the hand as a person, a pink cube as a cup, and again, those game cartridges as a cell phone, and then no mention of the sign in the background. So I'm going to quickly just switch this model to the VRSight model rather than the base one on Coco. Again, it's just a one-line change. And then rerun this system. And I guess I can also show the speed of which it takes to relaunch it as well.
Yeah, one of the things I was definitely wondering is what's the
Sure.
latency on the system?
Yeah, I have better notes in our paper, but we measured like kind of a realized latency of like half a second or less. I mentioned there, I saw one comment in the chat, like the frames per second dipping between like 16 to 25. In some cases, like if we're just looking at the edge detection in isolation, we're getting like 1,000 frames per second because it's just running on like base OpenCV code. But this object detection variation is just like measured like from a 1 frame basis on my computer, where I'm also like screen sharing to Zoom right now and running, other applications at the same time. We found that this variation is like still very usable and what we'd consider like real time, because when you're like the main thing that we feel like is important is if you are moving your hand like outside of a boundary, and then playing that sound effect immediately happens within like half a second, or it's less than that even. It's like I want to say it's like in an order of milliseconds for sure. Um, So if I don't know if we're able to hear the audio now, but if I press the scene description for this as well, and just I can also show the latency that which it takes to update this model. So if I drag it around, then we see the edge detection updates really, really responsively. The object detection takes a little bit more time, and the depth detection is super accurate, but takes the longest amount of time. We are caching each of these outputs. So whenever you press a key from the 3-key controller, it will just take whatever the most recent frame is that are synced up with one another. So if I say that I want a general scene description of what's here, we'll ask GPT to describe the scene. And then the description that we get back is a virtual hand is reaching for an interactive element with a notification and a sign visible nearby. So that is describing everything that's on the table, as well as the sign in the background that's currently identified as a UI element and a sign element at the same time. I think that this can get a lot better with just even more object detection examples. But
So
if we
one
then want to do the scene sweep, the second one, to read out all objects, there's 14 of them, so it'll take a little bit a little while. I won't keep everybody while they read them all out, but we prioritize this sign in the background being like, when you're ready to explore some new virtual worlds, insert a cartridge into the console. And then we read out each of the interactive elements. So like rectangular device, colorful screen, black and gold design, I guess is one of the like cartridges here. And then aim assist, the third option, will grab whatever's the most likely objects near your hand and then describe like this a controller that might be right next to it, or the cube that might be right next to it, and then give a more detailed description of like it's a pink cube basically, that you might be able to interact with, and then decide whether or not you actually want to pick that up or not.
So one of the questions I want to highlight here from Jesse, he says, one of my major difficulties in VR as a low vision user is simply navigating and reading UI, especially in an app or game. Can this help read and identify text and controls when in an experience, similar to how the new Quest screen reader does so on the dashboard?
Yeah, so I just saw that the dashboard came out the other day, but so I haven't had a chance to kind of compare and contrast, but the app is able to use like optical character recognition tools to read each of this text out, as long as it's like reasonably legible. And what I mean by that is like if there's text that's really far away, like somebody's name tag across the room, it might just kick back an error saying that it can't read it. We have some like safeguarding for that as well, that it doesn't just give you back garbage. But as long as it's like seemingly legible output, then it will be able to read like signs and UI elements Right now, you'll need to query for them. It doesn't read it out for you automatically, but that's one of those interaction design things we'd like to work on with people in the future.
Awesome. Some other questions here from Christina is the Discover dataset or trained model available somewhere?
So the DISCOVR dataset, we annotated it completely through RoboFlow, like an online like description tool or description service. I think Dylan's question was, did we do them all by hand? Yes, for most of them, and then we generated some augmentations to get the full number. But all of these will be available uh, at the same time that VRSight is available, hopefully later this month. Again, I'm waiting on most likely next month. We have received potentially good news about a conference acceptance, but I've been told I'm not allowed to announce it publicly yet. So keep an eye out for that. The link, I did go ahead and make a repo for it though, so it will be live on the Madison Ability Lab GitHub page, which I will post to everyone in chat. But there's nothing on it, so hopefully it will be there soon.
Awesome. And I will definitely put that on our XR Access GitHub because this is
Awesome.
obviously tremendously useful. Um,
Thank you.
in terms of running it, do people require just, sufficiently powerful computer versus some
Mhm.
amount of like tokens or money that goes to processing? Like, what are the requirements for that?
Yeah, so right now we have it modularized enough to where you can kind of put in whichever model that you'd like. I will not be releasing our Azure API keys, but we right now every time that we like use GPT, for example, we ask Microsoft Azure to get that response back. I think over the past like year of testing this, it's been like under $100 for like absolutely everything in terms of like token use. But the system should be able to work with just like on-device models as well. I was talking to some people at Kai who suggested swapping out some of the like GPT with more of like a VLM or other sorts of image recognition or video recognition models that aren't just asking a large language model or like a multimodal large language model for all of these different queries. So you would be able to run something that's probably similarly performant on device if you have the necessary resources for it. That's one thing with like using Quest, for example. Like you could use like Valve Index or other like SteamVR based PCVR headsets. But we chose one that runs standalone just so that we'd be offloading the like running the app to the VR device rather than also trying to run the app at the same time as the model because then we get into some performance bottlenecks there. Unless you just happen to have two GPUs, but we would like this to run on a gaming laptop. And we demoed it at Kai on a regular like Alienware gaming laptop from like 5 years ago. So
Awesome.
that's
And
the
then
goal.
our last question here, since we have to wrap up, from
Sure.
Michael Cooper. In your testing with users, how much were they able to accomplish tasks and how did they subjectively experience it?
Yeah, I think I don't have a number off the top of my head for like aggregate as a whole. I know that our menu tasks were a little bit, um, or I know that our like object recognition tasks and our how many avatars are in the room and what sort of objects are around you. Everybody performed very highly. The only sort of errors that we got were maybe they used that general scene description and then GPT added like a wooden gaming chair, which is not in the environment. And so that's what the user reported. But other than that, it was more like smaller detection sort of errors that we think that we can smooth out over time. Things that were a little bit like less useful were the menu pointing interactions, and I think that that really will maybe require like completely changing up how people like interact with menu-based interfaces because the whole like hand-eye coordination was really difficult for a lot of our users, like holding their hand up for a long period of time. Where it like read it out and then they were like, well, maybe not this one. And then they'd move their hand a little bit and then it would read it out quickly, but for each of these options, and then waiting for the haptic feedback from the controller to see, am I over a menu out? Like everything together was like maybe not the best interface method. So, in the future, we'd really like to invite all of you or other researchers or anybody else to really help us with iterating on this interaction design paradigms, as well as like having the ability for like an optimized Unity package or something like that, as Jacob mentioned in chat, just to allow developers to tag different objects. So that way we wouldn't have to rely on a computer vision approach. We'd just know that the object is there. Again, we didn't do a Unity package for this one or for this project because we wanted everything to be post hoc. And also Meta just doesn't let you run two apps at the same time on Quest, unless it's just like a browser-based thing in the background, which is how we're able to communicate audio back to the user. But it can't be like full applications with sensor headset data and everything, or controller data and everything like that yet. So yeah, I'm happy to like follow up with anybody else after the talk. And yeah, I recognize we're going a little bit over. So thanks again, everybody, for having me. And yeah, I'll pass it back to Dylan.
Absolutely. Yeah. Thanks so much, Daniel. We will be sharing all these links on Slack. Everyone, please make sure to join the Slack. We can continue the conversation there. But yeah, this is a fantastic solution. I think in a perfect world, we'd have full developer buy-in and full access to those systems. But in the meantime, having a post hoc solution, I'm sure will open this up to a lot of people. So brilliant. Thanks so much. And
Thank you.
everyone, please consider joining us later this month. We have our XR Access Roundtable number 2. So thanks all, and we'll see you then.
Thank you.